Hello everybody, let me introduce myself. I am Alexey Bobrovsky, I am scientific researcher at Chemistry Department of Moscow State University. First of all, I would like to thank the organizing committee for the possibility to give invited talk at this conference. The title of my presentation is related to photocontrollable liquid crystalline polymers for photonics. Now, a special interest presents the creation of different so-called smart materials. They react in a certain way to various external influences and change their physicochemical characteristics. These materials can be used for different applications in photonics. I would like to demonstrate to you one of the most promising types of polymer systems for creating such materials. These are photocontrollable liquid crystal polymers. The goal of our work is the creation of photosensitive liquid crystalline polymers and composites with controllable supramolecular structure and optical properties. This slide shows the main working principle of these polymers and composites. In the films of such systems, light can initiate a number of chemical reactions in photoactive groups. These reactions act as molecular switches starting in cycles of structural transformations. The main task of our work is to develop approaches to the creation of new, smart, photoactive liquid crystalline polymer materials that can be used in photonics, optoelectronics, information recording, display technologies, etc. Let me remind you the key features of liquid crystalline polymers. First, the liquid crystalline polymers are characterized by the combination of molecular self-organization and high anisotropy with the possibility of contactless control of their properties by electric, magnetic fields, light, etc. It should be noted that liquid crystalline polymers form the same LC phases that are observed in low molecular mass liquid crystals. The main types of the mesophases are shown here. The second important feature of liquid crystalline polymers is the ability to maintain the structure in a glassy state after external exposure. In the temperature range between the glass transition and transition to the isotropic phase, the various fields and light can change the structure of the phase or orientation of the molecular fragments. Cooling of liquid crystalline polymer film below glass transition temperature enables fixation of modified structure in the solid glassy state. For most liquid crystalline polymers, glass transition temperature lies in the range slightly above room temperature up to 100 degrees, isotropization temperature up to 200 degrees or more. The copolymerization of various functional monomers allows one to obtain a huge variety of multifunctional liquid crystalline polymers, combining functionality of different side groups. The main advantage of such systems is the combination of the optical properties of low molecular mass liquid crystals with the unique mechanical properties of the polymers, the ability to form films and fibers. This slide shows the main types of the investigated liquid crystalline polymer systems. The following fragments were used as the main building blocks: mesogenic, which are responsible for the formation of liquid crystalline phases; photochromic, capable of undergoing photochemical transformation under the influence of light; chiral groups, responsible for the formation of cholesteric, helically twisted phase; combined chiral photochromic groups that allow one to manipulate optical properties of the cholesteric phase. Using these groups, we obtain the following types of photochromic systems. First, these are homopolymers, double and ternary copolymers of the different structure. Then, ionophoric copolymers with crown SR fragments capable of complexation with metal ions. A new class of compounds, photochromic liquid crystalline dendrimers. For the first time, we studied the processes of photoisomerization and photoorientation in such systems. Polymer networks of various structure. A very promising class of composites is porous polyolefins, polyethylene and polypropylene filled with photochromic liquid crystals. And finally, a very simple type of systems which we have also obtained and studied, mixtures of polymer nematics with chiral photochromic dopants. What are the principles of photoregulation of the optical properties of liquid crystalline systems? This slide shows one of the photoinduced processes occurring in the films of photochromic polymers. These are photoorientation processes under the action of polarized light. Let us consider disordered or non-oriented copolymer film. During irradiation, photochromic groups perform isomerization cycles and finally oriented in direction perpendicular to the light polarization. I would like to note that this process is cooperative. In other words, mesogenic groups are also oriented together with photochromic groups. So, photoorientation leads to the appearance of anisotropy of optical properties of polymer films, displaying noticeable values of dichroism and birefringence. These types of photoprocess have found great application for the photoregulation of the optical properties of many types of polymer systems. You can find more information on this topic, for example, in our two recent reviews. Using this photoregulation principle, we have created new so-called common surfaces for the orientation of liquid crystals. For this purpose, a series of new photochromic polyamides with various site photosensitive groups based on azobenzene, cinnamic acid, and coumarin were synthesized. As I noted above, the irradiation of such films leads to the orientation of photochromes perpendicular to the plane of light polarization. If a layer of liquid crystal is applied over such film, then liquid crystalline molecules will be aligned along the direction of orientation of the photochromic groups. In other words, polyamide acts as common surface that controls the orientation of the liquid crystal. Moreover, by changing the direction of polarization of light, one can also control the direction of orientation of liquid crystalline molecules. This allowed us to record invisible images that appear only in polarized light. The obtained polyamides have a number of advantages compared with the already known photoalignment agents that was reflected in this patent. Now, let us consider another principle of photoregulation of optical properties, the photocontrol of the helix pitch of polymer cholesterics. The cholesteric phase is characterized by helical supramolecular structure. This structure selectively reflects light with a wavelength proportional to the pitch. N is the average refractive index. Such a structure is induced by chiral fragments, which are characterized by a certain twisting power beta. In order to realize helix phototuning, we have synthesized a number of copolymers and prepared mixtures with combined chiral photochromic groups. Irradiation induces isomerization and a change in the shape of chiral photochromic groups, for example, benzaldehyde-mentanon. This leads to a decrease in their helical twisting power, the unwinding of the helix, an increase in the wavelength of selective light reflection. In other words, we can control a color of polymer films. This approach allowed us to record color images. For such recording, polymer films were irradiated using mask. We have observed a shift in the peak of selective light reflection to the long wavelength spectral region. The magnitude of this shift can be very large. We realized the position of the peak from 400 nanometers to 2500 nanometers. And in our case, it is limited only by the spectral range of our spectrometer. Here is an example of a color image shown, yellow letters on a blue background. In the case of benzaldehyde-mentanon, photoisomerization is irreversible. However, for the azobenzene derivatives, we have realized cycles of selective light reflection shift during sequential UV radiation and annealing. In summary, we have developed a new approach for creating light-controllable materials for reversible and irreversible recording and storage of information. Note that the recorded image is stable in glassy state for a long time, for years. Using the same principle of the helix photocontrol, we have realized cholesteric polymer systems with phototunable circularly polarized fluorescence and laser generation. Introduction of fluorescent or laser dye molecules into the cholesteric matrix allows one to obtain circularly polarized emission or lasing from such films under light excitation. Usually, laser emission is observed at long wavelength edge of the selective light reflection peak. Introduction of the chiral photochromic dopants enables shift of both selective light reflection and lasing peaks. Lasing in oriented cross-linking cholesteric networks obtained by photopolymerization of planar-oriented monomeric cholesteric mixtures doped with the laser dyes was demonstrated. Holographic recording on polymer nematics and cholesterics opens unique possibilities for creating various optical elements and for image recording. We have for the first time performed a comparative study of the holographic recording of diffraction gratings on polymer nematic and cholesteric films. Such recording was performed using special setup by interference of two coherent laser beams. Relatively high values of diffraction efficiency were obtained, up to 30%. Moreover, the possibility of double recording of optical information was demonstrated for the first time. One recording is due to the photoregulation of the helix pitch, with letters are written in this way. Another one is due to the holographic formation of diffraction grating. Light diffraction on the grating is shown here. We have obtained a new type of liquid crystalline composites based on porous-oriented films of polyolefins. For the first time, we have used oriented porous films of polyethylene and polypropylene as polymer matrices. These films were filled with low molecular mass and polymer liquid crystals, including the molecules of various dyes and photochromes. It was found that the fibrillar structure of such polymers aligns the molecules of liquid crystals and photochromes. This allows the creation of unique photosensitive materials. In particular, we have created a new type of photoactuators, materials that convert light energy into mechanical work. These photoactuators are based on porous polyethylene filled with azobenzene-containing polymer liquid crystalline network. When such films are irradiated by UV light, isomerization of photochromic groups occurs in the top layer of such films. This process results in transition of nematic aligned phase to isotropic one. As a result, bending deformation of the film takes place. These processes, isomerization and bending, are completely reversible. Another type of the photochromic composites was prepared using porous silicon filled with nematic photochromic mixture. For this purpose, photonic one-dimensional structure was prepared from silicon wafer using electrochemical etching with controllable periodically modulated electric current. On scanning electronic microscopy image, you can see periodic structure of cross-section. Here a scheme of this photonic structure is presented. This structure also consists of cavity layer. Different diameters of pores results in different refractive indices of these periodic layers and produces one-dimensional photonic structure. In order to realize phototunability of this photonic bandgap position, we have introduced into prepared porous structure photochromic mixture based on nematic liquid crystals, pentathiazanbiphenyl, and azobenzene dopant. The main feature of this azobenzene dopant is reversible EZ isomerization, leading to extreme decrease in molecular anisotropy. Due to this decrease, irradiation with UV light induces isothermal phase transition from nematic state to the isotropic phase. Due to the presence of lateral methyl substituents in the azobenzene chromophores, photoinduced Z isomer possess very high thermal stability. Back transition from isotropic phase to nematic one takes place for about 40 days at room temperature. This makes the prepared photochromic mixture very convenient from the point of view investigations and practical applications. Here, the reflectance spectra of composite before and after irradiation are shown. UV radiation causes the redshift of the photonic bandgap and cavity mode by about 10 nanometers. This shift is associated with the increasing of the effective refractive index of the composite. Such increase of the refractive index can be explained if we assume that liquid crystalline molecules before irradiation are aligned along the axis of the pores. After UV irradiation and transition to isotropic state, refractive index slightly increases, resulting in redshift of photonic bandgap position. The observed spectral changes are reversible, and visible light induces faster recovery of the initial position of the photonic bandgap and cavity mode. Obviously, the obtained new LC composites are promising for the applications in photonics. In conclusion, I will focus on some recent results related to the study of the possibilities of modifying the surface relief and topography of liquid crystalline polymer films using light. The idea is to study the formation of various structures on the surface of films of azobenzene-containing polymers under the action of focused laser beams of different wavelengths. Here you can see the most striking and unusual result of our work. We have studied polymers with azobenzene groups containing lateral methyl substituents. For the first time it was found that irradiation with green laser leads to the formation of craters, while a red laser forms hills. The origin of such features formation is associated with photoinduced stress and heating under polarized light action. The obtained results demonstrate new possibilities of using light as non-contact method for the surface modification of liquid crystalline films. In future, these methods can be used for tuning of surface tension, adhesion, wettability, etc. Let me summarize our results. In our work, new approaches to photocontrol of the structure and optical properties of liquid crystalline polymer systems have been developed. In particular, we have obtained new common surfaces for liquid crystalline alignment, polymer cholesterics with phototunable helix pitch and realized color image recording, lasing in polymer cholesterics, diffraction gratings based on liquid crystalline polymer systems, double recording of optical information, photochromic liquid crystalline composites based on polyolefins, new type of photoactuators, new composites with phototunable photonic bandgap position, and recently we demonstrated new possibilities of photomodification of the surface of liquid crystalline polymer films. This work is carried out in collaboration with Russian and foreign research groups. We thank for the financial support Russian Science Foundation and Russian Foundation for the Basic Researches. Thank you for the attention.